All right, continuing section 6.3, we're going to look at the graph of log functions. So what I've got drawn here is a general graph of log y equals log base a of x, and this works for any a we want. So it has this general shape to it. The domain, if you look at it, the domain is everything from 0 to infinity, but it never touches 0, so it's going to be a open parenthesis on both sides. So let's see, the range is everything from negative infinity to infinity. So we're going to say all reals. Now, one thing I should say about this, over here, it does grow to infinity, but logs grow really slow. If you were to compare the growth rate of this, it looks a little bit like square root, but square root, if I were to draw it in, would outrun it. Logs are slow. And it passes through this point right here. This is the point 1, 0. Why is that? Because remember, anything to the 0 is 1. So log base anything of 1 is 0. So they're all going to pass through that point. And I didn't write it out on here, but it's going to have a vertical asymptote at the y-axis. And some interesting facts down here. This first one is the one I really want to sort of concentrate on, because the other two facts below are consequences of this. If f of x is log base a of x, then the inverse is, and I've got an error here, it's not e to the x, the inverse is a to the x. We'll talk about e later. But let's look at this. If I take this and I graph y equals, let's just pick 2 to the x. If I then put in y equals log base 2 of x, I get the inverse function. Remember, inverse functions are reflections of each other across the line y equals x, and we can see that here. You can also see this purple function. It looks pretty much like what I drew, although I think my drawing was a little too, was growing a little too fast. And let's see, if we change this, I'm going to change this to a. Add a slider. Notice when a is 1, it's not really graphing much. But let's make this go from 2 to 20 in increments of 1. So these graphs are reflections of each other, so they're inverses. All right. Let's hop back over here and look at this. The other two rules, remember, if a function is an inverse, or if two functions are inverses of each other, they undo each other. So we get this, log base a of a to the x, the log and the exponential just undo each other, and you just get back x. And same thing over here if you do it in the other order. A raised to the log base a, excuse me, I'm yawning, of x is x. And sometimes I think it's beneficial to write this, maybe not with an x, but with a box. Because you might have an x in there, you might have something more complicated in there, or you might just have a number. But whatever's in the box here is also going to be in the box over here. So I've got a handful of examples. Simplify this thing. Okay, 3 to the log base 3 of 10, that's just 10. And note, this only works when the base and the base of the exponent and the base of the log are the same. So that one's 10. This one down here, 5 to the raised to the log base 5 of 25. Yeah, it's just 25. All right, let's see. I skipped over problem 2 here. 2, notice there's something different going on here. You've got log base 2 of 8 to the 10. Now those bases are not the same. So you can't just say the answer is 10. What you have to do is first rewrite the thing inside. I want to rewrite this as 2 to some power. And we can do that easily here since 8 is a power of 2. So here's what we'll do. We'll rewrite this as log base 2 of 8 is 2 cubed to the 10th. So what we have is log base 2. Now a power to a power, you multiply those powers, so you get log base 2 of 2 to the 30. So we get 30 for our answer here. And now something similar is going to happen on number 4. The log base 3 of 81 to the 10th. Well, 81 is 3 to the 4th power. You see 81, your first thought is probably 9 squared. Well, it's 9 squared, it's also 3 to the 4th. So what we've got inside of here is 3 to the 40th. And so the answer to this is just 40. Okay, this last one down here, number 5. I didn't leave myself much space. I'm going to move it up slightly. Sorry, that's not easier if you have a printout there. But let's see, log of 100 to the 999. Let's see, 100 is 10 squared. Notice one thing. This is coming up. If there's not a, if there's no base written here, it's implied to be 10. So this is log base 10. 100 is 10 squared to the 999. So 2 times 999 is 1998. So the answer here is 1998. All right. Let's look at this a little more, talking about the 10. A logarithm with base 10, they come up a lot, and so they've got a special name. They're called a common log, and it's written just as log with no base. So let's do several of these. Log base, or log of 10. Well, it says 10 to what power is 10? The answer is 1. Okay, this next one, log of 0.00001. So what do we have to multiply 10 by, or what do we have to raise 10 to get this? 0.00001, this is a 10th, 100th, 1000th, 10,000th, 100,000th. So this is going to be -5. Now another way I could do that is I could use my calculator. I haven't used this one in a while. But let's see, I've got my TI calculator here. And the way that you would do this is you just put in log, where's my log button? Here it is. Log of 0.0001. It gives me -4. It's doing that because I left a 0 out. So I get this, and it gives me it gave me an error. But when I actually put the right thing in, it gives me -5. Now that's actually interesting. When I did log of 0, it gave me an error. Error domain. It's because the domain of log is 0 to infinity, but not including 0. If I try to take log of a negative number, say log of -5, it gives me a similar problem. It says non-real answer. And if you have a different calculator, it might give you something else. This calculator, yeah, this one I did log of -5, it just gave me math error. So anyway, we're going to need the calculator to do these last two examples. These last two examples here are let's see, let me switch back to it. There, here we go. Log of 1100. Now, here's the deal. Log of 1000 is 3. Log of 10,000 is 4. So what about log of 1100? Well, it's going to be between 3 and 4. And it's going to be closer to 3 than 4 because 1100 is closer to 1,000 than it is to 100,000. So let's see. I'm just going to do that on my calculator. There's not really a better way to do that. Log of 1100. When I put that in here, I get 3.04139 ... All right. Now this last one, log of 990,000, that's just a little under a million. A million is 10 to the 6th. So we should expect this answer to be just under 6. I'm going to guess 5.9 something. But let's see. Log of 990,000. Yeah, actually 5.9 something was right. It's 5.9956, etc. All right. So with those, we pretty much had to use the calculator. You might say, how did they do this before they had calculators? Well, before calculators, like the way an engineer would do something like this would be to either use a slide rule or a table of logarithms. And we'll learn some rules later that'll let us do some stuff that they might have used. But actually, computing logarithms was one of the early things that was done with computing devices. Napier. If you look up Napier's bones, if you look that up on Wikipedia or something, you can read about some early tools that were made for calculating logarithms. But let's that's the common log. That's one of the two that we use often. The other one is the natural log. The natural log is the logarithm that has e for its base. And the way we write that out is ln. So if you have ln of x, that means the same thing as log base e of x. So what is e? Some of you have probably seen it, some of you probably haven't. So let's talk a bit about what e is. It's an irrational constant, a lot like pi. It's called the Euler number because it's named for Leonhard Euler. E comes up a lot of the time when you're dealing with exponential growth, or if you're dealing with, well, some other places it just pops up, interestingly, kind of like, same way pi pops up a lot. But the value of e is here. It's it's easy to remember the first several decimals because it's 2.7. Then you've got two 1828s here together. And then the next one are like the angles of a triangle, 45, 90, 45. But there's no pattern to it. Just like pi, it's an irrational number. But e is important. So let's do a few examples here. Now e is 2.71, etc. So natural log of e, I'm going to do that on my calculator. I'll do the first one actually showing you. Let's see, you got natural log of 3. When I hit that, it gives me 1.0986. Which makes good sense. 3 is just a little bigger than e, so it makes sense that e to the, that would be, e to the, it makes a little sense that we'd have to raise e to a number a little bit bigger than 1 to get 3. Now e squared is, what is it? E squared is 7.389, etc. So natural log of 10, we'd expect that to be a little bigger than 2. So natural log of 10, sure enough, 2.30, etc. And natural log of 100,000, well, I don't know. I can't even estimate that really. I'll just stick it in my calculator. It's 11.51. 29, yada, yada, yada. All right. I know this video is getting long, but I want to do one last quick thing. And this is just kind of an extra. But I want to show you, where does E come from? There are two ways you can talk about the origin of E. One of them is this. If you do 1 plus 1 over x, and you raise that to the x power, when x grows large, this approaches E. So notice here it's 2.6 something. If I take this and I slide way over, it's getting close to there, 2.71, etc. I guess I could also do this. Instead of putting in x there, I could put in a, and I could put a in here as well. And now if I put in large values for a, put in, say, 1,000, it's getting close. And I can keep going and adding in more numbers here. It's kind of amazing the computer can do that so quickly. But anyway, that's one way you can say where E comes from. The other is this. If you take a to the x, I equals a to the x, we get this. I want to make a bigger than 1, so let's put it over here. And I'm going to change this to f of x. If we look at the slope of this, which this is something you'll see in calculus, but if we look at the slope, that's what this f prime of x, that tells me the slope of the blue graph here. And if I start moving this around, if a is, say, 2, notice the slope is less, the slope graph in red is less than the green graph, the blue graph. If I switch it to 3 or 4, it's bigger. 3, it's kind of hard to see, but it's barely bigger. E is the place where those two graphs lie exactly together. And that's a big deal in calculus, but you'll see that next semester. All right, that's it for this video.